Hello and welcome you all. I guess you are, yeah. Okay. Hello, welcome you all. I am Mohammad Moniruzzaman Bapari. I'm actually CTTC chair of Bangladesh chapter. Today we have the privilege to host the distinguished lecture, Mr. Krishnan Viswanth. So we are destined to start at 7:30 Bangladesh time. So let's get started. Quick biography of Mr. Krishnan Viswanth. Mr. Krishnan, an IIT graduate, began his career at Voltas Limited, a Tata Group of company in 1977. After 15 years in diverse roles, he founded his own enterprise in 1992, specializing in air, fire, smoke management products. A fellow of ASHRAE and a member of ASHRAE for over 3 decades. He has served as ASHRAE president, contributed to several committees, and received multiple distinguished awards. Widely recognized as a lecturer on room air distribution, Krishnan has conducted seminars and training programs across India and internationally. So let's not get wasted any time, and let's give the floor to Mr. Krishnan.
Thank you. Thank you for that lovely introduction. I'm very happy to be here with all my friends from the region at large. I'd like to start sharing my screen now. So here we go.
Yes.
Ashad, good evening.
Hi, good evening. How are you?
I'm very good, Ashad.
Okay.
Thank you.
Thank you. Thanks.
Okay, so I hope all of you here are able to see my screen. And I'm extremely delighted to be here with all of you because I may know some of you from our past association in the region at large. So it's always a privilege and a pleasure to come back and speak to all of you. So today we're going to speak about the topic that's been given really is something that's very close to my heart. But before we dive into this, what I'd like to do is to one second. Yeah. Okay. So what I'd like to do is to run a few slides, which is kind of mandatory for us to do as a part of the ASHRAE Distinguished Lecturer Program. So this particular presentation is brought to you by the ASHRAE Society, CTTC. And I must give this caveat that whatever we present here do not necessarily reflect the policies or the position of ASHRAE or the Bangladesh chapter, along with all the other chapters which are co-hosting this program. My request also to all of you would be to silence your phones and avoid any other distraction so that you are able to focus completely on what we're going to be talking about for the next couple of hours. If you need any more information on the ASHRAE DL programs, please do visit the website that's mentioned here. Always remember, all of you as ASHRAE members, and I'm presuming that all of you who have joined us today are all members of ASHRAE at your respective chapters. Remember that ASHRAE is a people-to-people society, and it really thrives on the volunteerism and the voluntary contributions made by members like all of us. And there are several opportunities for people to come and contribute, and ASHRAE looks forward to that. And remember, each one of us brings our own individual ideas to the table, and that's really what helps ASHRAE to keep growing. So do find your place in ASHRAE, visit the website, look at all the offerings that the society has by way of technical committees, and you will be able to then find your niche in the society. So with those words, I'd like to once again thank the host chapter for picking a theme like this, that talking about IAQ. And remember that this is the presidential theme of the year, and the person you see on your screen is our society president, Bill McQuaid, and his theme is healthy buildings. designing for life. That's his theme. So when you are trying to design a building that is healthy, of course, all buildings are meant to be designed for its occupants, which are the people. And so, okay, I just want to ask everybody that you're able to hear me loudly and clearly.
Yes, we are.
Okay, great. So all buildings are being designed and built for people. That is something that all of us must understand. And since they are meant for people, we want to make sure that the people who occupy these buildings remain healthy all the time. And for them to remain healthy, it's essential that we design our buildings also to be healthy. One of the key components of any space that we occupy is the air, because that is what we share with all our co-inhabitants. Typically now, whether you are sitting in your workplace, or you're sitting in your office, or you're driving home in your car, or you're sitting at the house, the air that is inside all these occupied spaces is what we are sharing with all the people who occupy these spaces with us. Just to give you a broad idea of what the outdoor air pollution looks like, this is what the world pollution map looks like. And what is shown here is the PM 2.5, the particulate matter 2.5 microns level. And you can see that the countries in our region are particularly affected, as they seem to have a much higher level of PM 2.5. So if the outdoor air is of this nature, which carries with it a higher level of PM 2.5 concentration, then we need to be really worried, because when we are designing buildings, our objective is to get in air from outside to be able to ventilate our spaces. So if the air from outside has a higher concentration of pollutants, then we must ensure that those pollutants are first addressed before they are allowed to come into the occupied space. So this gives you an overall context of where we are. All of us have heard of terms like air quality index. So what does the air quality index really mean? The air quality index represents the average concentration of all the items that's listed here, which is typically particulate matter 10, PM 2.5, nitrous oxide, ozone, carbon monoxide, sulfur dioxide, ammonia, and also lead. So based on the average concentrations that are represented here, an AQI index has been developed. So you can see the good, it's categorized as good, satisfactory, moderately polluted, poor, and very poor. So many of our urban cities in and around, let's say, India or Bangladesh or Pakistan or places like that, we would find that the average air quality, it tends to be between moderately polluted and poor. That's because of the kind of pollutants that exist in and around our outdoors. It might be better in some areas. For example, if you look at the AQI range in different parts of the world, for example, the first band that you see is what is in the United States. Now, each country has its own band by which they classify. For example, in America, if the AQI is more than 300, it's considered hazardous. But in India, we say that if it's 250 and above, then it's severe. We don't even get into the hazardous range. But look at Australia. So in the case of Australia, they find that their satisfactory and moderate to poor regions are much better than what we have in our country. Now, what is the cost of poor air quality? How do we really address this, or how do we kind of put a value to this? Is to say that, okay, how many people die in a given point of time due to various reasons, starting from things like terrorism, war, opioid overdose, homicides, AIDS, malaria, obesity, and you find that the number of people who have died is of that order, say about 2.5 to 3 million in the case of obesity, which is much more than what a war or terrorism really does. Look at this now. You'll find that air pollution is the single most contributing factor for deaths worldwide. Though you might find doctors don't directly attribute a death to air pollution, they might simply pass it off saying as, it's a cardiac arrest or organ failure, but the root cause really remains air pollution. And that's why we need to be very wary about the kind of air that we are providing to all the occupants in our spaces. And we as HVAC engineers who are actually designing occupied spaces and constructing them, we need to be more mindful about the actual quality of air that we're going to provide to our occupants. Sometimes people ask, what is worse? Is indoor air quality worse than outdoor, or the other way around? And what is more important to us? Now, you must realize that in today's context, all of us, whether we look at ourselves or we are talking about our children or our parents, we find that 90% of our time we are spending indoors. Now, that when I say indoors, it could be at home, it could be in the office, or even commuting to work and back, you're spending with closed confines. Maybe with other people, maybe alone. So what does it really mean? It really means that by the time you reach the age of 50, you really would have spent 45 years of your life indoors. Now, this probably wasn't true about 40, 50 years ago. Typically, like for example, when I was growing up, as children, we would spend a lot of time outdoors playing games and things like that. We would walk to school and stuff like that. But in today's context, you find that, especially in urban environments, play areas are shrinking, and therefore children spend a lot more time indoors than they would like to do outdoors. Sometimes parents will tell the children, don't go out because the air quality outside is poor. So they're forced to really spend 90% of their life in closed spaces. This is something that I wanted to share with all of you. And I hope that it will strike a chord. There are two pictures that you see side by side. And what we are doing here really is measuring the quality of air indoors as well as outdoors. Now, this picture was taken in Bombay, where I live, and it is taken during the festival time of Diwali. So when you see the picture on the right-hand side, you'll see firecrackers going on. Now, because of all those firecrackers, one would expect that the outdoor air quality would be poor. But when you look at the numbers on the screen, you'll really see that the pollution level inside seems to be higher than the pollution level outside. And that really is contributed due to various factors because of outdoor air coming in unfiltered, and also the incidence of your volatile organic compounds, etc., mainly formaldehydes being generated within occupied spaces. All this contributes to a poorer air quality. So many a times you will find that the indoor air quality probably is more severe as compared to the outdoor, especially when you don't have proper ventilation and you're relying on air conditioning like split units, which is constantly just recirculating the air without any outdoor air. So this is something that we need to be all mindful of. Remember, at home, when we are doing cooking, we tend to use an open flame, and that flame can also contribute to increased nitrous oxide emissions. So what is the problem? The problem really are buildings. And the building operations really are responsible for most of the CO2 emissions. And the unhealthy buildings that affect our lives, our health, productivity, and our overall well-being. And all this really started off way back in the 80s when people started talking about the sick building syndrome. where people would go to work apparently in good health, feeling all good. And when they return back home in the evening, they find that they are feeling a little unwell. And after a lot of study, it was really found that it is probably because people are spending a greater portion of their time during their working hours inside spaces which does not have the access to good outdoor air. So the same recirculated air is being used all the time, and therefore the air quality inside is dropping. And this actually led for some amount of research from ASHRAE's side, and that's how the early standard 62.1 evolved. This is a quote that I like to share with everybody. Dr. Joseph Allen is a well-known professor at Harvard. And what did he say? He says, improve lighting, ventilation, and heating or cooling in office buildings can actually boost workers' performance and productivity. And therefore, developers, architects, and businesses are becoming increasingly interested in healthy buildings. That word healthy is the key. And that is really the presidential theme this year. So, what really contributes to a healthy building? So, the first thing is ventilation. Then, of course, you need to look at thermal comfort. Then you look at noise, air quality, moisture. Of course, we also need to worry about water quality. We need to look at lighting levels. And last but not the least, the safety and security of all the occupants. Now, all of you are fully aware that the United Nations has already mandated that getting access to good quality drinking water is a fundamental right for everybody. Hopefully, very soon we should also have a UN charter which would say access to good, clean, healthy air is a fundamental right for everybody. And that's what all of us should be working towards. So the single most contributing factor to the health of the building is air. Now, all of you who are part of the HVAC fraternity will realize that the air is the most complicated challenge that we face. Because the air has diverse properties, and all of us as HVAC engineers, it's our prime kind of occupation to make sure that this air is treated, filtered, cleaned, and then provided to the occupant inside. And there are various things that help us to do this. So, what are the basic factors involving IAQ? We talked about particulate matter. Then there is temperature. There is humidity. Temperature and humidity is what most HVAC engineers are very familiar with, right? So we talk of temperature, we talk of RH, and that is what we really focus on when we are trying to design an HVAC system. But now we need to really focus also on things like particulate matters, volatile organic compounds, and CO2 levels. Now, this graph here actually shows you the monthly mean CO2 concentration, and we are going back as far as 1960. So, when in 1960, when these kind of parametric measurements first started, the outdoor global CO2 level was less than 300 or thereabout, 300 ppm. Today, when you look at 2025, we are seeing that the global outdoor CO2 levels are close to around 420 to 450. Of course, this might vary from place to place, but this is kind of an average number that you see. This might seem familiar to all of you. How many times have we sat in meeting? I hope nobody is feeling like that today, sitting in this particular presentation. Sometimes people say, oh, you know what, people are getting bored because the presentation isn't very good. So I hope you're not feeling like that because of my presentation. But if you are, then probably you might also want to look at what is the quality of air in that room. This is really what happens when you get into a conference room. At the start of the conference, everything is fine. But when you stay stuck up in that conference room for maybe about half an hour or 45 minutes, with the kind of occupancy being present in that room, you will find that the CO2 level has risen substantially to make you feel very sleepy and tired. I actually got this article which appeared in the January issue of the January 2025 issue of our ASHRAE journal, where Dr. Gursaran Mathur has written an excellent article on cabin CO2 in automobiles. Now, if you see this chart on the left-hand side, you can see how the CO2 concentration builds up in an automobile. And you see those four lines, you have the blue line and you have the orange line. So that represents the number of people in the car. So if you have 4 occupants and you start driving off, within about 20 minutes, the CO2 level would have reached about 6,000 ppm. Now, it's not just sufficient to say 6,000 ppm is a lot, which is, if you look at the ASHRAE, the 62 limit, approximately about, say, 1,000 ppm as an acceptable limit, then you can see we are way beyond that. But it's also important to note that if you have 4 people sitting in that automobile, no matter how large it is, what is the percentage of air breathed out by one person is being breathed in by another person, right? So that is really how you have to start worrying about spread of infection. The one on the right side, again, it shows you how the CO2 can build up in the space depending upon what is the kind of speed that the car is doing. And why the speed matters is because as the speed increases, the leakage, body leakage tends to drop down. When I say body leakage, I'm talking of the automobile body leakage. And again, a new car versus an old car, if the car is new, then the leakages are less. So if you're driving an old car at a moderate speed of about 50 to 60 kilometers an hour, then your body leakage increases and therefore the CO2 build up is also reduced. So this is a very interesting article, and I'm sure that all of us today are driving around in automobiles, and when we are driving in urban environments, we always tend to drive with our glasses rolled up and with the air conditioning on. Of course, most automobiles will also provide you some kind of a button which says that you can get in outdoor air instead of just recirculating. But the hazard of doing that in an urban environment, for example, in Bombay, where I'm driving literally bumper to bumper, if I keep my recirculation off and get air from outside, I'm going to be breathing in a lot more of carbon monoxide and sulfur dioxide, which is going to come into my car from the exhaust of the car in front of me. So these are things that we need to worry about. So next time when you're driving, always make sure that you stop by the side, roll down your glass, let the air be replaced, and then start driving off, especially when you're doing long distance driving. So what are the studies that have been done in this field reveal? It says that for every 400 ppm increase in CO2 levels, your cognitive function drops by about 21%, which means your ability to think and make decisions are impaired. And this has really been tested out by Harvard, where they got a couple of chess players, and when I say chess players, not average players like you and me, but they got some of these grandmaster types to come and play chess. And then they monitored and they adjusted the pollutant levels like CO2s, like VOCs, etc. And they actually found that with the increase in these kind of pollutants, the mistakes that they were making started to increase. And that's how these numbers were arrived at. So what does poor air quality does? It gives you drowsiness, fatigue, loss of concentration. And that's the reason I will again take you back to that slide which I showed you about automobiles. Many of these accidents that happen during the night when people are driving long distance, people say, oh, he fell asleep. And that's really not because the person hadn't slept the previous night or whatever. Many a times it happens just simply because of the CO2 levels in the car have gone up dramatically. So all this can really lead to unfortunate incidents. PM 2.5. Why does PM 2.5 become a big issue? And these things started gaining traction and attraction, especially after the pandemic. You know, when we were all facing the threat of COVID, we realized how some of these particles most of the particles that you breathe in will get arrested by your upper respiratory tract. But some of these particles, which are very fine, like 2.5 and less, they tend to go right into your lungs and get absorbed directly in the bloodstream. And that's what creates the problem. Apart from that, you also have your volatile organic compounds. And volatile organic compounds are something that you find all around you, especially in occupied spaces. So if you look at the picture on the left, all the furniture that you have, your cosmetics, laminates, the clothes that you wear are also degassing all the time. They are emitting volatile organic compounds simply because they've been washed overnight using some detergents. People use air fresheners, plastics, carpets, all kinds of adhesives. For example, in the office, we use printers, we use copiers. All these are actually emitting VOCs. So we need to make sure that we are monitoring and measuring these pollutants. Once we are able to monitor, measure, and we can identify where these sources are, we can try to figure out how we can best eliminate this or reduce its effect on our systems. So again, these are some numbers that a 500 microgram per meter cube increase in VOCs will reduce your concentration and cognitive abilities by about 13%. So what is the best way for us to make sure that we are able to improve our quality of air inside? First is to source control, which means we must identify what is the source of your pollutants. So when you do continuous monitoring and you're able to measure the various parameters like VOCs, 2.5, CO2, etc., and if you are able to arrive at a pattern, and then if you're monitoring it widely, you will be able to decide and arrive at what the source is. And the best way to reduce pollution is to eliminate the source. Of course, it might not be possible for us to do that all the time. So what are the other alternatives? The best alternative known to all of us in the HVAC industry is that we can reduce the pollution by dilution and ventilation. So when you say dilution and ventilation, there are several standards that are known to us. You'll find not just in ASHRAE, but even outside of ASHRAE. Some standards will talk to you about having different air changes for different applications. Some will tell you that you can have a combination of air changes. For example, if you look at within ASHRAE, we have ASHRAE standard 170, which talks about ventilation standards for healthcare environments. And it provides you for different kind of applications, what kind of air changes you must maintain. If you look at the very recently launched standard 241, it again talks about air changes. But really the most definitive standard for ventilation and for breathing zone outdoor air is standard 62.1. And I'm sure that all of you who are in ASHRAE and in HVAC practice are all familiar with standard 62.1. We can do a separate one-day program on 62.1. It is as wide and diverse. But what I'm going to tell you today is a few key features in 62.1, which all of us are familiar with probably, or should be familiar with, that helps us to arrive at what is the actual required ventilation airflow that is to be provided to each of the spaces. And 62.1 gives you two options. It doesn't really talk about air changes per se. But what it says is that, okay, what is how is the pollution in the space caused? It's caused on account of two factors. One is the people themselves, and the other is the space itself. The space will comprise of various things, like, we talked about earlier, things like furnishing and laminates and carpets and so on and so forth. So 62.1 provides you a kind of a prescriptive number that says how much of CFM per person you should have, coupled with CFM per square foot of the space. So that's why if you see in this equation 6.1, the breathing zone outdoor airflow is a product of the number of people multiplied by the CFM per person plus the area multiplied by CFM per square foot. Both this together will give you the total zone outdoor airflow. So this is a table that provides you for various kinds of spaces that you are designing. See on the left hand side, for example, I've just taken a small extract, but it runs into a couple of pages where you'll find all kinds of application. And it gives you what is the amount of CFM per person that you should have, and what is the CFM per square foot for the area. These are default prescriptive numbers. You could use these and simply say that as per the standard, this is the minimum ventilation that I require to provide. Now, apart from this, 62.1 also says that merely putting that number by itself is not correct. You need to actually figure out, if I calculate some air quantity, let's say for a particular space, I say that based on the number of people and the area, we arrive at, say, 500 CFM. So how do I ensure that that 500 CFM of outdoor air, which I'm bringing into that space, is actually being distributed uniformly to all the occupants? Now, you can ensure that by making sure that the air distribution system that you have will be able to meet and comply with certain requirements. So there is something called as air distribution effectiveness. Mind you, we're not talking efficiency yet. We're talking about effectiveness. So it gives you different types of air distribution systems that you could have. For example, the one that's most commonly used is a mixing air system. So in the mixing air system, you've got, how the air will be supplied from the top of the room, and then it is kind of mixes in the entire space, and the return air is then collected back on the ceiling, or it could be collected at the floor level. So depending upon how the air is being distributed, you have something called as the zone air distribution effectiveness. So if the zone is well ventilated or the air is absolutely well mixed, then the ventilation effectiveness will be 1, which means if I calculated CFM based on number of people and the area was 500 CFM, then I simply divide that by 1. That is for a well mixed air distribution system. But look at row 3 here, for example. If I've got a situation where I'm supplying warm air at about 15 degree Fahrenheit or more above the room temperature, and from the top, that is from the ceiling, and my return is also on the ceiling, then obviously what happens is, because the air is warmer than the room air temperature, then the air will tend to stratify on the top. So obviously, that air which you are saying is the outside air doesn't really reach the occupancy level at the lower level, and therefore the ventilation effectiveness is identified as 0.8. These are prescriptive numbers. So if this is your method of air distribution, then instead of 500, you will have to 500 divided by 0.8. You got it? So that means you need to supply roughly around 17% more of the outdoor air. So typically, instead of 500, you probably end up putting around 585 CFM or there, something like that. So what it means is If your air distribution system is not effective, then you will need to bring in more outdoor air. So there is a penalty you pay, because especially in places like, say, Dhaka or Bombay or Madras or some places like that, where your outside enthalpy is very high. And when you're taking outdoor air and bringing it in, conditioning it, and then bringing it in, if you have to bring in more air, obviously the amount of energy you will spend is going to be greater. And therefore, you want to make sure that your room air distribution effectiveness is 1 or higher than 1. So can we get it higher than 1? Of course you can. That is, if you use distribution systems like the stratified air distribution system, which is shown over here. You can see that you can achieve as much as 1.2 or 1.5 simply by choosing the kind of air distribution system that you would like to employ. For example, we have systems like displacement ventilation, or you will have underfloor air distribution, which can yield numbers of 1.2 to 1.4 very comfortably if they are well designed and put into operation. Can we go better than that? Today's context, people are talking about what we call as personalized ventilation systems. To give you a very rough idea of what we mean by this is, for example, when you take a flight and you sit in an aircraft, and you have a little nozzle on top of your seat, which you can actually adjust to get the blast of air right onto your face. That is like a personalized ventilation system, where the outdoor air can be brought directly into your breathing zone. When you do that, you will be able to get an effectiveness of 1.5, 1.6, even 1.7, which means you need to bring in only about 30 to 35% of outdoor air as compared to what you would in case of a well-mixed system. So therefore, the choice of an air distribution system will decide how much of outdoor air you can bring in and how well it is distributed in the space. How do we distribute air in the space? Typically, we use ducts, and all of you are familiar with ducts, and you can see there are all kinds of ducts that are available to us, all shapes, all sizes. You can get them insulated. You've got fabric ducts, and the good thing about fabric ducts is they look very colorful, and you can pull them down, wash them, put them back, unlike the metal ducts that you see. You can put the ducts on the floor. We talked about underfloor. So you can also run the ducts below the floor. When you do ducts, there are some things that you want to be careful about. How you route the ducts, for example, look at this particular plenum here, which is being fed by this duct. Now, when you run a duct like this, obviously the amount of air that's going to exit this plenum is going to be severely throttled. Because of the way the thing is flowing. When somebody is designing the system and installing it, the installer probably doesn't realize that when he does this, it is going to impact the airflow. So obviously, when the airflow is impacted, the actual air distribution effectiveness in the space is going to reduce. So therefore, if you started off with a certain outdoor air, that would be inadequate. Okay, you saw the outside of a duct. What about the inside of the duct? You'll be amazed that these are some pictures that I've got from ducts after they are in operation for about 5 to 6 years. Sometimes you can get this state even after 2 to 3 years, depending upon the kind of dust loading or the levels of filtration or the state of maintenance. So what it tells us is that if that's the state of the duct inside, no matter what we talk about IAQ, etc., it's not going to really help, because this is going to make all of us feel very sick very soon. Of course, nowadays you have access to duct cleaning. So in this picture here, you can see what the duct looked like before we cleaned it. And now this is what it looks like after we cleaned it. So obviously this is what we want, like over here. This is what it was before, and this is what it is after. So all of us must take cognizance of the fact that ducts can get dirty. And most of the time, the air inside the duct is saturated. So there is moisture and there is also dirt and dust. And with moisture, dirt and dust come dust mites and becomes a breeding ground for colonies of bacteria and microbes, which are not really good. Therefore, we need to be very careful about how we clean our ducts, how we maintain our ducts. This little picture tells you how we are actually distributing air in a space, which is the normal mixing air system. So here you have a unit which is located on top, and then we are supplying the air from the top. It comes down, mixes, picks up the heat, and goes back. This is your return, and it goes back on top. So this is typically how we are conditioning spaces. So this air which is coming from here is treated. It's got outdoor air, it's got return air, a mix of all of that. When we do this, we also need to worry about how we are supplying the air into the space because draft is something that can make all of us feel very uncomfortable. So when we design spaces, we want to make sure that the room air distribution is such that it keeps people comfortable, doesn't make them feel very cold. So that is our objective, to keep people comfortable and to make sure that the quality of air that they're getting is something that is going to foster good health within the space. These are thermal comfort factors. This is not something that we are focusing on in today's discussions, but the factors that affect thermal comfort, there is one is the speed of the air, what is the relative humidity, what are the radiant temperatures, and of course, two factors. One is metabolic activity and personal clothing. This is something that will vary from people to people. So depending upon your build, the kind of food you eat, the place where you come from, all this will contribute to how you feel, whether you feel comfortable or you feel uncomfortable within a certain temperature range. We want to make sure that the air that we provide inside is within the range of about 40 to 60%, because it's found that it is this optimum zone that helps to prevent the growth and spread of bacteria, viruses, fungi, etc. So I'm sure that all of you are very familiar with these numbers. So now let's look at what are the different types of having seen what worries us in terms of air quality. Let's try to see what are the different types of air distribution systems that are available to us that will help us to make sure that we can provide a good indoor environment for people. So the three types of systems or that are most commonly used. One is the mixing air. Mixing air system is the one that's most widely used. 90 to 95% of the spaces you walk into will have a mixing air system. Whether you use a room air conditioner, whether you use a split unit, or whether you use a package unit, ducted units, invariably they're all mixing air systems. Then, of course, we have displacement underflow. And of course, lastly, we will talk about the personalized ventilation system as well. So in a mixing air system, what happens? Now, we have supply air, which is brought through this duct, and then it diffuses into the space, and then it spreads like this. And as this air exits this outlet, it does so at a fairly high velocity and has a fairly high delta T between the room temperature and the supply air temperature. So this causes the room air to mix with it. It induces this because since it's coming at a high velocity, it creates an area of low pressure along the boundary layer, and that low pressure will draw the room air into it, and therefore the air mixes. And so if you want the entire space to be well mixed, you must pay careful attention to where you will locate your supply air outlets and how many of them you will require to make sure that you have a good spread index that covers the entire occupied space. You also want to carefully think about where you will exhaust the air from. If I were to put this return over here at this point, then a lot of the supply air would just go back without coming into the space, without coming into the breathing zone. And therefore, my ventilation effectiveness gets compromised. So I want to make sure that my sealing plan is laid out in such a way that I am distributing the air uniformly based on the load requirements, and not many people make this mistake of distributing air on a square foot basis. Identify where the loads are located, where people are sitting, and then decide where you should place your supply air outlets. And then make sure that the return air inlets are located such that there is good mixing and ventilation in the entire space. So here you have an office, and then you also have a lab. So you can see that that's your air handling unit. That's the outdoor air. It's drawing in the amount of outdoor air required. It gets treated, filtered, and then it is being distributed to the 3 zones. There is return air being picked up here. It's being picked up here. Now, in this last room, obviously, there is a lab. Some kind of experiments are going on that is releasing some fumes. Now, you don't want this fume to come back into these spaces. So what you do here is that you're making sure that this area remains under negative pressure and all these fumes are exhausted out. Now, whatever is being exhausted out, that's the air coming into this space, that needs to be compensated. So that compensation happens via the relief air here and the outdoor air here. So this outdoor air is based on number of people, square foot per person, etc., plus whatever is going out from here and here, so that proper air balance is maintained. This is really how a full-blown mixing air system would work, no matter how large the space is. To distribute the air in the space, you have various kinds of supply outlets. Here are some which are very common. All of you are familiar with all this. An outlet like this, or this has got adjustable louvers. The advantage of having these adjustable louvers is that you are able to guide the air and deflect it to places in all corners of the space, so that you are able to get good ventilation effectiveness. As opposed to that, if you use an outlet like this, you're really not able to make any adjustments at the side. These are what you install on the ceiling, like I showed you that thing earlier. Some more outlets which go on the ceiling. These are what we call as slot outlets. These are outlets which you will use in large open areas where you want to throw the air over very long distances. The important thing is to understand the geometry of each of the outlet, understand how does the air exit these outlets and how does it perform in the space, and you must do the selection based on the performance characteristic of each of these outlets. The problem with this is that many a times we tend to go by architectural appearances. If the architect says that, hey, I like the look of this outlet, let's go with this, it might not be the one that's most suitable, right? So what you really need to do is to identify the one that's most apt for a particular application, and then do the selection based on the performance characteristics which the manufacturer would provide you. If you fail to do that, then you will land up with a system which will provide you very poor ventilation effectiveness. For example, here is a picture where we've got, I talked about an outlet like this, which we used to throw large quantities of air over long distances, which means the discharge velocity of the air from these outlets is very high because it has to throw over a long distance. But when you put them on the ceiling, and no matter, even if the height is, if you're talking about 10 meters, the discharge velocity is high, the temperature of the air leaving the outlet is much lower than the room, and therefore gravity begins to play a big part. So with the high outlet velocity, the air tends to accelerate further because it is dropping down. And that creates a very, very uncomfortable situation for people sitting in this space just below. And I've seen this in many areas. The other issue in this particular application is you can see that there are these ducts which are carrying the supply air, and that is directly blasting the air downwards. And you could see these ducts which are alternate. You don't see any grills or anything here. Why is that? That's because that's supposed to be the return. Now, you don't see any grills here, but that's because the grill is placed on the top. So you can't see it. And you see this metal roof? So what happens in the summer, that roof gets heated up. This is blasting cold air down into the occupied space. That return air which is being picked up by that grill on the top is at a very high temperature, very close to the skin temperature of that roof, which in a place like Bombay, the outside temperature goes as high as about 98 to 100 degrees Fahrenheit. Now you can imagine what happens to the people here. They are all feeling very cold because this is blasting down. But the air which is going back into the air handling unit room is absolutely warm, with the result that the coil is always or the air handling unit is always in a mode which is cooling continuously, because it is sensing that the return air temperature is very high. Therefore, a lot of cooling is required. And therefore, the valve on the chill water valve always remains open. Now, very difficult to control the inside conditions with this kind of design. So you must be very careful how you distribute the air distribution system. This is something again which is very common. I'm sure that all of you would have come across this. We put linear grills on the ceiling and we blast the air down. So as HVAC engineers, we would execute a project like this and go away. The architect goes away. The poor customer who's sitting below that grill is very uncomfortable. So what does that person do? He or she simply takes a piece of paper and covers that grill like that. First of all, it looks very ugly. Number two, by doing this, the person who's sitting below, his or her problem seems to be temporarily solved. But what happens to the air? The air simply moves into the next outlet. So after some time, the person sitting next, he or she then starts to feel very uncomfortable. So the problem never really gets resolved. Have you seen this? This is because this is something that I actually saw in a hotel lobby at the entrance. There is this outlet on the ceiling right in front, right on top of the reception area. And every time that front door would open, there would be a big gust of warm, humid air that comes in. It hits that outlet, and then you have all this condensation that happens. And very soon over here, you'll see black marks, fungus, and growth that is happening, which is going to contribute to the poor air quality in the space. And then, of course, you have this constant problem of water dripping on the table or on the floor. Somebody has to be constantly cleaning it. So these are things that you need to be very careful to make sure that there is no ingress of outside hot, humid air into the conditioned space where your outlets are located. When we make four-way diffusers like that on the ceiling, the idea is that we use a principle called the Coanda effect, which actually helps us to spread the air uniformly on all the four sides. Sometimes it leads to what is called as smudging. That's because the air is not well filtered. But some architect came out with a clever suggestion that why not we put a coving like that on all the four sides so that the smudging gets eliminated. Well, they did manage to eliminate the smudging, but what they did do also at the same time was they disturbed the entire Coanda effect, and therefore the air started to dump straight down instead of diffusing. So people sitting below that diffuser started to feel uncomfortable drafts. So, excuse me. So you need to be very wary about doing things like this. That's what I said. When you see an air distribution outlet, it performs in a particular way. It is intended to perform like that. It's engineered to perform like that. So don't try to change that, because then it alters the entire operational philosophy of that product. This is something like the square diffuser. Every square diffuser, for it to work effectively, will need a surface alongside, so that the air can then come and travel like that and then go down. When you don't have a surface adjoining the square diffuser or a round diffuser, then the air tends to dump down. You will have the air coming straight down like that. So this is not an outlet which is designed to be installed on an exposed duct like this. If you have an exposed duct, then really speaking, you need to look at an outlet something like this, which is called as a swirl diffuser, which does not rely on the quanta. It relies on simply swirling and mixing the air. So if you have an application which has an exposed duct and no false ceiling or no surface adjoining it, then do consult the manufacturers to find out what would be the right kind of an outlet. And an application like this, really a swirl diffuser is a very effective outlet. Now, if you see the picture on the left-hand side, if you look very carefully, you can see that these outlets, even the plasticine wrappers, which the manufacturers has packed and sent, has not been removed. Somebody has commissioned this plant. So you can imagine what happens. It's just that when somebody, it's like buying a car, and when you buy a car, you get your seats all wrapped up in plastic. And there are many people who say, oh, let's not remove the plastic because the seats will get damaged, right? I don't know how comfortable it is to drive with the plastic sitting on a plastic cover. And this is what they seem to have done here at the air outlet. So how effective can the ventilation be if your supplier outlets get blocked like that? So you want to be very careful about that. What has happened here is you've got these jet nozzles to throw air over long distances, but because the architect felt that it needs to be masked, should not be seen, they have gone and put some grills in front of it. So obviously now this is going to really create a lot of turbulence and also mar the throw, which means that you can't get the proper effectiveness. I talked to you about how ducts need to be put properly. Now you see here, this is the kind of bend which has happened. Okay. I told you about having no ceiling and an outlet. So here is a swirl diffuser, no ceiling, good choice of an outlet, but its effectiveness is reduced simply because of the way we have connected the duct. So we need to make sure that even if we choose the right product, we must make sure that it's installed correctly. When I say installed, not just the diffuser itself, but also the connecting pieces to the plenum that you see over here. This is a lovely example of how you can actually do heating and cooling using the same outlet. During the summer months, you have these swirl diffusers, which is swirling the air and pushing it right down into the occupied space after mixing it well. But when the heating time occurs and you want to supply warm air from here, how do you ensure that the warm air goes right down to the occupied level? If the swirling action is not sufficient to take it and it might stratify, you can think of using these fans at those times. Also, at certain times during the cooling season, if you find that the occupancy has gone up substantially, and what you can then do is to use these fans and increase the air velocity over the people, and therefore be able to keep them comfortable. So these are also methods by which you can intentionally increase the airspeed to keep people comfortable. Now, one of the best ways of trying to make sure that you get the right amount of the outside air and delivered into the space is by trying to decouple the load inside the space. All of you are familiar with load evaluations. when we do load evaluations, we have a sensible component of the load, a latent component of the load. Now, a large part of the latent component of the load comes from the occupancy of the people inside, unless, of course, you have certain processes. But by and large, in commercial occupied spaces, a large part of the latent load comes from the outside air and also from the occupants. So, what we do really is to decouple the loads. So, we have, for example, there is a simple, on the left-hand side, you will see a simple example of one zone where we have an outdoor unit and an indoor unit. This is simply taking, like you have a split unit. So this is simply taking care of the space sensible load. And then you have an outside unit which is bringing in the tempered supply air from outside. Okay, this is the outside air, and then there is a exhaust air. So this exhaust air, there is a heat recovery that happens, and then the outside tempered air which comes in. You can have in multiple zones like this. So here you have a dedicated outdoor air system. There is a fan, coil, etc. that cools it and brings it into the spaces. And each space can have different types of cooling system. This can have a simple VRF. This can have a different type of unit, and this can have an air handling unit. And depending upon what kind of system you have, the outside air can be directly funneled into the space. For example, here you have a duct that brings in directly into the space, and this is your unit that's taking care of the sensible load. Typically, for example, you can also visualize a hotel room where you have a fan coil unit, and you have a separate unit which brings in the treated air. Here, this treated air can be mixed along with this air or here. So this gets, the return comes here, mixes with the outside air, and that comes into the space. So this is what we call as a dedicated outdoor air system. This can get more complex as the building gets bigger and bigger. For example, here is one situation like that, where we got outdoor units which are catering to all the spaces, and you have one dedicated outdoor air system which is bringing the outside air, treating it, and then supplying it to the various floors. Now, you can decide how much of this should go into each space depending upon what is the actual requirement. So once you do your load evaluations, you pretty much know how much of it is required where. And you can have different types of, for example, here we got chill beams. So we have a dedicated outdoor air system that is bringing in the air and supplying to the chill beam directly. Okay, so this is one method by which you can actually have a dedicated outdoor air system that can treat the outdoor air and admit the required quantity into each space. And we can go one better by saying, how do we actually control this? For example, in this space, we got, let's say, 2 classrooms here. And in these 2 classrooms, one has got less number of students, the other one may have more number of students. So obviously, the one that has got less number of students will require less amount of outdoor air as compared to the one which has got more students. So what do we do in that case is we use something called as demand control ventilation. So what happens then is that the dedicated outdoor air unit will supply as much air that is required for each floor or each space, depending upon what is the demand. How do we evaluate the demand? Well, in the case of outdoor air systems, as we said, we can calculate it based, what is the variable here? The variable is the space doesn't change in terms of square foot. So therefore, the CFM per square foot, that part remains fixed. But what varies is the number of people. So if the number of people are less, we will supply less air, as is illustrated over here. So demand control ventilation allows us to provide as much of outdoor air that is required. How do we monitor this? We could monitor this based on occupancy sensing or occupancy counting, or we simply go by what is the actual CO2 level in the space. The higher the CO2 level, that gives a good proxy for us to decide how many people are within the space. Higher CO2 concentration means higher occupancy level. Or if space-generated volatile organic compounds are more at that point in time, requirement of higher outdoor air. So that's that component that we talk about. So we need to then measure what is the CO2 level, what is the VOC level, etc., and then decide how much of outside air will be pumped into that space. But in most cases, the ventilation demand is based on occupancy, which means based on CO2 level. But like I said, if your indoor pollutant like a VOC concentration is also going up, then you could also modulate that outside air based on VOC demand. So how do you modulate this? Okay, so this is really how it works in today's context. Everything is controlled through the BMS. So you simply have systems like this, which is measuring, and based on that, modulates the amount of air that comes into each space. So here we use what we call as terminal units. So what are these terminal units? These are generally used with all mixing air systems where it's nothing but a damper, but the damper is getting an input from two sources. One is it can get an input from a set point. This set point could be the room temperature, or it could be the room CO2, or it could be the room VOC, right? And it is also getting an input from the actual amount of air that is flowing through the space. And then it, based on the kind of programming that you feed into it, it will allow the exact amount of air that is required to meet your set point value. Just to give you an example, let's say that there is about 500 CFM of air going through this duct, and that's being measured. And then let's say the set point is based on CO2 sensing. And we have said that, look, if you want to maintain a set point of 800 ppm, which is acceptable within the space, we need about 500 CFM. Let's say that in that space, the occupancy levels have gone up, the CO2 level has gone up, and it has gone to, let's say, 1000 ppm or 1200 ppm. At that point in time, this controller will give a feedback to this actuator here, which will allow this damper to open up to increase the ventilation. And it will open it up to the extent required to bring the CO2 levels back to the set point value. So this set point could be either CO2, or it could be VOC, or it could be temperature, whatever. So these are the kind of devices that you can think of using. Now, apart from keeping the people comfortable, providing good air quality, by varying the actual amount of air going through it based on demand, you are able to actually modulate the speed of the fan. And all of you are familiar with fan law, which says that the power consumed varies as the cube of the speed. So if I am able to reduce the airflow when it is not required, reducing the airflow means reducing the speed of the fan. I'm also able to save a lot of energy. Therefore, this device not just helps you to meet your energy conservation requirements, it also helps you to optimize your air quality and thermal comfort within the space. Typically, that's what a terminal unit would look like. And you can have a terminal unit with multiple outlets. So that's what we use. We use mixing air systems. We can use that with a dedicated outdoor air system. We can couple that with a demand control ventilation to make sure that your amount of outside air that you bring in after all your detailed calculations is provided in the right quantity at the right place, so that the air quality within is optimized. Now we come to the next set of type of air distribution system, which we call as displacement ventilation system. How does this really work? Now what you see in this room is a typical overhead mixing system. So there is an outlet diffuser which is placed on the ceiling. The air exits, comes like that from all the sides and mixes with the room air. Typically, we supply the air at a temperature of around 55 degrees Fahrenheit to keep your room at about 75 degrees Fahrenheit. And the outlet velocity is high, and the air is supplied from a point which is far away from the occupied zone. Typically, the occupied zone would be up to a height of about 6 feet from the floor level, and the diffuser is, or the air outlet is installed at the ceiling level, maybe about 12 feet, 13 feet, or 14 feet. So that's how a mixing air system works. But in a displacement, we do exactly the opposite. What we do is we supply the air directly into the occupied space, which means the supply outlets are placed in the room at the floor level so that the air comes directly into the occupied space. Since the air is coming directly into the occupied space, we want to make sure that the temperature of the air is as close to the room temperature as possible. So if we are maintaining the room at about 75, then my supply temperature would be around 68 to 70 degree Fahrenheit. Since the air is again coming directly into the occupied space and we do not want drafts, typically we said that for people to feel comfortable at about 75 degree Fahrenheit, the air velocity should not be more than 50 feet per minute in the cooling mode. So if the air is directly coming into the space, then the outlet velocity should be not more than about 70 feet per minute. Okay, so this is the kind of system that we are looking at. So as the air leaves the outlet, it is still at a lower temperature as compared to the room temperature. Therefore, it is slightly heavier than the room air, and therefore it settles down to the floor. So what is going to drive it? It is the heat source within the room that will push the air forward. So the air remains stratified, it doesn't mix. So these are our basic fundamental assumptions in room air in a displacement system. So as the air leaves the outlet, the air from the back pushes the air in the front, much like a piston. So the air at the back displaces the air in the front, and that is why we call it a displacement ventilation system. And it kind of moves around the room, it goes around the obstacles, and it will stay tight to the floor. The air doesn't mix up, nothing happens, the temperature is lower, therefore it is denser, therefore it stays there till it encounters a heat source. Once it encounters a heat source, it will start to warm up, and as it warms up, the air will rise up. It creates what we call as a thermal plume. And this thermal plume will continue to rise, and as it rises up, it draws the room air with it and takes it up to the ceiling, from where it gets exhausted out. So if you see the temperature profile, you will see the temperature at the lower part of the room in the occupied zone is comfortable, whether it's pretty hot right up on top near the ceiling. So let's take a look at what it looks like. So here you see the cool air enters the space and it spreads along the floor. So it is just moving forward at a very low velocity. It spreads evenly across the floor. It can go around obstacles. Nothing comes in the way till it comes in contact with a heat source. Now this is a heat source, and the air gets warmed up, and as it gets warmed, it rises up. And you can see that thermal plume over there. So here you see a person, a human being like you and me, and there is that air at about 68 to 70 degree Fahrenheit. And as it encounters a person here, it starts to get warmed and it will start to rise up. Now imagine that this cool filtered air enters the space, and you can see the thermal plume being created, and it comes into your breathing zone. It is not mixing with the room air. So the quality of air that you get is much better than what you would in the case of a mixing air system. That is why we are saying that the ventilation effectiveness in a displacement is approximately 17% less air is required. We say the ventilation effectiveness is 1.2. So here is another view. The cool air cascades onto the floor, and the black thing you see is a picture. Let's say it's a human being or a heat source. It gets warmed up, and then it comes into your breathing zone. So the air that you breathe is the cleanest air that is possible. It's clean, filtered, and that is coming directly. Unlike a mixing air system, where all the pollutants in the room are getting mixed up, and then you are breathing that air, right? So if you have a room like this with two human beings, each of you is getting the same good fresh quality of air, unlike the air which is mixed in the room. So if the air is mixed in the room, each person's pollutant can get mixed, and you can be breathing and sharing that air. So that is the basic difference that you will see, as is illustrated over here. The displacement has a more efficient contaminant removal, and therefore it gives you ventilation effectiveness as 1.2. But like I said, how well you design this will also decide whether it is 1.2 or 1.4. We have seen systems which provide effectiveness as high as 1.4, which means you require roughly around 33% less outdoor air than you would in case of fully mixed system. These are the different types of outlets that you can get. The only thing that you need to worry about is, especially in places which are humid, where humidity tends to be an issue, is since you are supplying the air at a temperature of around 70 degrees Fahrenheit, it might mean that your air is not being dehumidified adequately in the coil. Therefore, you need to have a method by which you can lower the temperature to dehumidify and then maybe add a little bit of reheat. So just to make sure that you get the temperature up, but to make sure that the moisture is completely removed. So it's always a good idea to consider the pros and cons of how much of energy would you save. But primarily here we are focusing on air quality, and therefore we are saying that the displacement ventilation is a great way for us to provide the cleanest air in the space, and thereby help us to reduce the amount of outdoor air that we will require. So that was a fully stratified system. Underfloor air distribution will help us in two ways. It's not a fully stratified system. It's partially mixed and partially stratified. So if you see the way the system works, you'll get a better understanding of that. So what we do is we create a false floor, just like you have a false ceiling. We create a false floor, and we can either pressurize the entire false floor plenum with the clean conditioned air, or we can have ducts running below the false floor to make sure that the air is distributed. So what we need here is we need some special kind of outlets which will swirl the air and spread it on the floor. But you see this zone, there is some amount of mixing that happens. So we always so once that air spreads onto the floor, then it behaves like a stratified system and gives you the same ventilation effectiveness. So all the care that you need to do is to make sure that you don't have people sitting in this vicinity. Okay, so if somebody is sitting here or somebody is sitting here, then it works extremely well, so that people are getting the best quality of air, and you also make sure that you save a lot of energy. Now we come to the other method, which is our personalized ventilation system. Now this is something that is slowly getting traction. So far it's been largely relegated to the kind of research zones, but now we are finding increased acceptance, and it is being used in many commercial applications. So just to give you an overview of this, what we do is we also have a duct which is bringing in the air and directly feeding into the breathing zone. You know, I referred to the aircraft earlier. So this is something similar to that. So this is only bringing in the outside air, whereas the rest of the room load is taken care of by a normal system like this. Or you could have something like this, where you can have the underfloor, like what you just saw, and then this person's body heat, etc., is taken away by the thermal plumes, and the outdoor air is being brought directly into the breathing zone. So these things actually get built into the furniture. For example, like this, you see this lady here, she's got her console, she's working on it, and this is your personalized ventilation outlet. Nowadays, they are also talking about, taking care of the, for example, you could have this furniture constructed in such a way that that could act as a radiant panel that can pick up the heat from the body, and then you get a direct ventilated air coming directly into your breathing zone. So there are several methods of doing that. Or you could also look at, instead of using outlets like this, you could have radiant ceiling panels. So that's another way of also taking care of the heat from the room and provide direct breathing outdoor air for breathing purposes. So this is also what can be applied in a healthcare environments. So you can imagine that when we are doing this, the actual amount of outdoor air that we require will be much, much, much less. That's why I said you can have an effectiveness of something like 1.6 or 1.7. So you really require only about 20 to 30% of the outdoor air as you would in a normal case. So this is slowly getting traction now, and people are paying attention to personalized ventilating systems. Also applied in healthcare environments where the patient is getting the out air directly here, and the return air gets picked up, and therefore there is no amount of absolutely no sort of infection spread that happens. So it's a great way to control infection without taking recourse to other methods. So this is what we actually saw today. To summarize all that we learned, this is your basic mixing air system where the air comes from the top and is exhausted out. So what is happening is all the pollutants, everything is getting mixed up in the room. We can control the amount of outdoor air by bringing in a demand control ventilation, where we bring in the right amount of outdoor air based on occupancy levels. Then we improve that system by using something like your stratified systems or a displacement where the air is brought in from here. So they get to breathe the cleanest air instead of the fully mixed polluted air. And then we went one better now with personalized ventilation systems like this, which helps us to make sure that using room air distribution, different methods, we are able to arrive at different methods of optimizing our air quality. Another thing that I want to leave you with is the use of chill beams. There is something called as a passive chill beam where we don't have any fans or anything. All we have is a cooling coil which has got chilled water circulating in it. When I use the word chilled water, I want to be a little careful here because the temperature of that coil should be above the dew point of the room. So what happens really is a convective process that happens. The air in contact with the coil will cool down, and because it's cooled down, it will go down, drop into the space, and then as it picks up heat from the people and the processes or whatever is happening inside the space, could be a fabric load, etc., it will get warm and rise up and again come and recirculate. So that's called as a passive beam because we're not using any fans or anything. This is extremely good when we want to make sure that people are comfortable without any drafts, especially if you're using something for, let's say, a playing area like a badminton or something like that, where you don't want the shuttle to be moving around because of the air velocities. The only drawback here is, as you can see, there is no way by which we can get any outside air in. So to overcome that, we have something called as the chill beam. So what do we do here? We have the same coil, which is taking care of the room sensible load, and we use a duct to bring in the outside air, which is treated to take care of the breathing zone air. And that is admitted into this chamber through specially designed nozzles. Now, as the air exits this nozzle at a high velocity, it creates an area of low pressure behind the coil. And that area of low pressure will tend to draw the warm air from the room into the coil. It comes, gets cooled, mixes with this air, and then leaves it like that in a coanda, and this mixes with the room air properly and then keeps everybody comfortable. Again, we want to make sure that our control systems are such that this dew point of this coil is always above the room temperature. So there is no condensation there, which can create, with condensation, you can have water collecting, or you have to have a method by which you have to pump it out. But the coil will be wet, and we want to avoid that. Because the minute you start talking of a wet coil, then there are several ASHRAE standards like 189, etc., which will tell you that if you have a wetted coil, you must filter it. The minute you start things like filtration, then all this will not be possible. Therefore, we always have to use what's called as a dry coil. So therefore, the temperature of that coil has to be above the dew point. So we need to make sure that you have proper control systems. And you're getting a good amount of outside air to come in. So this is generally used well in conjunction with a VAV unit that I showed you, which can modulate the amount of outdoor air required based on occupancies and things like that. So this is what an active chill beam is all about. And I've got a picture of a active chill beam under test here. So this is the beam, and that's a coil here. And this is the slot through which the air will exit. And this is your duct, which is bringing the outside air. So we're just doing some measurements in terms of velocities and noise, etc. So you can see the air is actually exiting from these two and then spread. So you need to have this ceiling so that it can actually spread across the entire space. So that was my last slide. And I must thank all of you for listening to me very patiently. And I would now like.
Thank you, Mr. Krishnan, for carrying
and
on. It's very
I
interesting.
hope you found this useful. If there are any questions on
Yes.
anything that I talked about today, I'll be happy to take it.
We got exactly time for 2 questions. If you
Whatever
have
number.
questions,
I don't mind if you want to extend it by 5 minutes.
please raise your hand.
Actually, first, I want to say it is really excellent and exceptional presentation because of yeah, you see your graphical slides with animation and which are really necessary for us. And so that our members also highly engaged with your presentation.
Thank you.
What we found in our member group, really, it is really nice from your presentation, what I found. And also you have provided requirement of IAQ and also countries data, live data, which we are unknown, and especially year distribution requirement
Right.
for, and also for the year distribution, whether that is really too much important, not only for the outdoor air, also for the HVAC load, also
Yes.
impacting.
Right.
So one one curiosity from my side.
Yeah.
Do you have any other presentation like year distribution, selection, procedure, sizing? Then I can request our CTTC chair to provide this.
Just to confirm, we are going
Ah,
to have another session with Krishnan
okay.
on very same topic that you are saying. It would be on next Saturday, hopefully.
Oh, it's really great, really great. You, one of my another question about I saw your in page 22 and or 25 regarding the score, like percentage. That I little confused about this. The score percentage, like carbon dioxide level for 400 ppm down or something like that. That I'm a little confused.
Okay, so let me just bring that back. You said
25 or 25 pace.
You're talking about this?
Yes, some score
Okay.
level.
Yeah, so what these are all studies which have been done at Harvard. Okay. So what they have done is they have got people like you and me sitting in a room, and they do certain tests by varying the concentration of pollutants in the space. For example, a very simple test that they carried out, which was very widely publicized, where they got the the active grandmasters of chess to play chess in a room, where they actually kept modulating the CO2 levels. So what they found was that, and how do they arrive at these scores is based on the number of mistakes that they were making. So if they improved the air quality in the room, they found that the mistakes that they were making were much less, right? And these are all statistical studies which they did, based on which they arrived at these numbers. So it is not something that it was done without a proper test method. So they had a room full of people uh, doing certain activities, and based on the actual air quantity, they monitored how the performance was. You know, uh, so otherwise, what happens is a very simple method that which you and I can actually evaluate, and that is you go to a meeting room, you sit there for a long time, you tend to feel sleepy. And Ershad, you have seen this many times. We sit in so many meeting rooms in ASHRAE, and sometimes you feel very sleepy or drowsy. It is not necessary that the speaker is not engaging or the topic is not interesting. It is just that the air quality in the room has become so poor that you tend to feel drowsy and sleepy. The minute you come out of the room, you feel fine. This is something that you can observe yourself if you put into any of these circumstances. But these numbers that I talked about are actually based on studies which was carried out by uh, the Harvard School. I hope that answers your question.
Yes, thank you. Thank you, sir. However, your presentation
Yeah,
is so attractive, so that we are really attentive with your presentation. If it may fall 4,000 ppm, maybe not impact. Just thank you, sir.
yeah. Hello, sir. Can I come in, sir, please?
Yes.
Yeah, my name is Badru, the CTTC for ASHRAE Nigeria chapter. Thank you so much, Krishi. It's been a long time we have this type of presentation, sir. One thing I needed to clear is with the air distribution and the essence of maintaining humidity range to keep indoor air quality in place, we know that dew point is a very important factor here. How do you relate that particular factor of dew point for different applications to be sure that we have the actual indoor air quality? Because the air distribution stands like our blood in the system. Without that, we cannot have effective exchange of heat transfer. So the issue is the dew point, which is very essential. How much can we get that done without a different weather level to be sure we are in good place? Then another problem is that our relationship with architects. Architects will just want something, but our own is to provide the right thing. So please throw some light, sir. Thank you so much, sir.
Please unmuted, please.
Krishnan, anything on the question in response?
I need to yeah, okay. Can you hear me now?
Yes.
Okay, so
Yes,
so
now hearing. Yes, thank you.
yes, so the thing is that when you design any space, you want to make sure that you ensure that your dew point is around 57, 58, designed for that. That will make sure that there is no moisture that it can condense into any of your surfaces. So it's always good to design based on a dew point. Not many people talk dew point. Everybody talks RH and temperature. But I would really speaking go back to the psychrometrics and design a space based on dew point. Ensure that you are always designing for about 56, 57 dew point. And then make sure that the supply air temperatures are such that you are not really, leaving any space for. The biggest problem, Badru, is that you have moisture into the space. Now, if you maintain the right dew point in the space, you will make sure that the vapor pressure is such that there is no moisture in ingress and condensing. So take care of that. That's all that you really need to do. The second point that you raised about is how do you deal with architects? Well, that's something that I've been trying to do for the last 50 years. It's very difficult. Very rarely do you get architects who appreciate what you say, because for an architect, well, at least most of the times, all they're interested in is the internal aesthetics, because that is what they get known by. So very rarely you come across an architect who would like to have good services, which can make sure that the customer's comfort is optimized. So it is for us to actually educate them about the importance of things like air quality. For many years when I started my career, it was always the architect who would tell you that, okay, here's the building, cool it. And that's it. And cooling meant the lower the temperature, the better it is. But now, especially in the wake of the pandemic, people are discovering importance of air quality. And with so much of standards and so much of programming that is being done, especially by all our ASHRAE chapters, where we are focusing on air quality, and our current president's theme is on healthy buildings and air quality. I think it will help if we go and educate people. And I must tell you, just about 2 or 3 weeks back, I was in the city of Hyderabad in India, where they hosted the World Healthy Building Conference, and you will be amazed. I made some presentations there, and we had a room full of architects. And after they sat through a presentation, they said, hey, we never knew about all this. Nobody told us. And my response to them was that we tell you, but you don't listen, right? So it is for each of us to understand these concepts and educate people. That is the only way we can spread awareness about this very important thing. And like I said in the beginning, the thing should be to get a UN charter to say that all of us as human beings deserve a fundamental right of breathing clean air. So that's what I want to say.
Our next question will be from Mr. Faber Oliad.
Thank you so much, sir.
Tell me.
Thank you very much, sir, for a wonderful presentation.
Thank you.
I want to ask you this question on air distribution in a room.
Yeah.
So if you are distributing air where you have a supply air terminal and a return air terminal, and there's a side of the room that has a window, is it advisable to discharge the supply air from the side that is close to the window, or you put the return air terminals on the side of the window?
Oh, well, yes, that's an
Do you understand?
interesting question. But you see, it will all depend upon if you're supplying from the other side, you want to first of all make sure that that air is not going to hit the window, because if that cold air hits the window, then you're going to have a lot of condensation outside, and therefore the purpose of having a window which is going to allow you to look outside, that gets defeated. But if there is a window and there is a lot of radiant heat coming in, it might be a good idea to make sure that you put some return air there so that you are able to pick up all that heat and take it away before it comes into the room. You do get special outlets which you can install even on top of the window, where you can have create a kind of an air curtain-like effect which can prevent the radiant heat from coming in. So these are all different types of outlets. That's what I mentioned. It's very important for us to look at different outlets and pick the one that's most suitable for your particular application. That I think is my answer.
Thank you very much. Our next question is from Mr. EMP.
Yeah.
He's stand for a long time. I don't know the name, but it's
Doesn't
EMP.
matter. Yeah.
So if you have any question, please throw it.
EMP, please unmute yourself and ask your question.
I think we're not audible. Okay. Few question is there in the
How,
chat.
how can we get the copy
Hello.
of the?
Out.
Oh,
Good
there is.
evening.
Yeah, we
Hello.
got it. EMP.
This is AMP, please. My name is Peter ASHRAE, and I joined in from Nigeria. My
Okay.
question is this: when you were talking about mixed air and you were talking about displacement method of air
Yeah.
distribution, you displace from the low level in the room,
Right.
close to the floor.
Yes.
And you were talking about the benefits of it over the mixed air,
Right.
having less VOCs and CO2 and the rest. But from my own understanding, like my office, they scrub it like twice a day with chemicals.
Mhm.
Most of the things that emit VOCs are
Yeah.
mostly at the floor level, up to the
Right.
mid-level of the room, the
Yes.
furnitures and the rest. So
Right.
how does this displacement pattern of air distribution is superior? How is it superior to that of mixed air? If it takes
So
all these chemicals from ground level up to your nose and you inhale it.
yeah.
Thank you.
First of all, if you are very sure that you've got all these surfaces in the room which are emitting these VOCs, the first thing is you need to do source control. Because if you don't do source control, then no matter what type of system you use, whether you use displacement or you use mixing, you are going to make sure that those pollutants are going to be there in the room. So the first thing we need to do is to do source control. I do understand that when you are going to do the cleaning, etc., then you will have these, especially all the cleaning agents which come into the room and are being used, they will release a lot of VOCs. So the important thing, that's what I said, you must do monitoring to find out when this occurs. So ideally, what most offices do, they would do the cleaning, etc., in the night, and then what they do is they will continue the ventilation for about an hour after the cleaning is done to make sure that it's diluted and all the air is exhausted out. And again, in the next morning, if the office starts to function at 9, you want to have the ventilation system starting up at 8 o'clock. So that you make sure that the system is completely flushed. So by the time the occupants come in, you will find that all your pollutants have been removed. Now, this is true regardless of whether you use mixing air or whether you use your underfloor or whether you use displacement. These are practices that you will have to do after you monitor. So once you monitor on a 24-hour basis about what are your pollutants, how do they peak, and what is the source, first thing is to try to eliminate the source. And second thing is to see how best we can dilute and ventilate the space so that when people come in to sit and work, make sure that the pollution levels are within the acceptable bands. That's what I would suggest.
Thank you very much, Mr. Krishnan. Our next question will be
Thank
from
you.
Hashmutuzzaman Bhai. Hashmutuzzaman Bhai, please unmute yourself. Our next question will be from Mr. Hashmutuzzaman Bhai. Yes.
Hello.
I'm trying to talk, but
Yeah, we can hear you now.
can you listen me?
Yes, of course. Loud and
Yeah,
clear.
yeah. Thank you, Mr. Krishnan, for your nice presentation and speech. In fact, you know that our country, especially the Dhaka city, is full of pollution.
Right.
So there's a indoor air quality. It plays very important role for ourselves,
Right.
as because we are highly sufferer. And ASHRAE, you have already explained in your slides that role of ASHRAE for maintaining our indoor air quality. And in fact, I work on pharmaceuticals industry as well as hospitals. So I know the impact of indoor air quality, how much it is important for us, and how ASHRAE can play roles. So thanks for clearing the rules of ASHRAE, especially that what I want to mean that ASHRAE have very important role for maintaining our indoor air quality. And I would request you to keep continue this. It is not only a lecture; it's in fact mentoring ourselves. So I
Very
would
true.
request Mr. Manoj Jaman to arrange another program on this ASHRAE and on indoor air quality or something. And also, I got many requests. I have seen many requests from your audience. They want to have this either video or recording of this of your presentation or slide share. I would request Mr. Manoj Jaman to arrange sharing this one and keep it up. I came to know that next Saturday we will arrange one. I shall attend it. Thank you again. Thanks, Mr. Krishnan, as well as thanks to ASHRAE Bangladesh chapter for.
Thank you. Thank you for your kind words. Thank you.
Ashwat bhai, our next question will be from Shekhar bhai.
Thank you, Mr. Monirujaman, for arranging such a nice CTTC deal, and thanks a lot to Mr. Krishnan, who has delivered such an insightful presentation with so many graphical presentation, including so many animations to get understand clearly. But I have a question regarding the cooling through floor level. In some cases, the cooling through floor level is very important, but in a building where there is a lower floor which is not actually maybe well conditioned, or there is no air condition for a long time, but at the upper floor where there is the cold air is passing through the floor for the ventilation through floor, how to actually avoid the condensation of the lower floor? Should we make any insulation on that floor where there will be the cooling with the floor level cooling? Could you please?
Yeah, so Shekhar, you're absolutely right, because when we are doing underfloor, it is there are two issues here. One is, of course, as you rightly mentioned, the condensation on the floor below. The other thing is that if the floor below is not air conditioned, then there's going to be a lot of heat that's going to come in from below the floor.
Yes,
that's going to add to your load, right? And that will raise the temperature of the supply air after it has come out of the cooling coil.
Yes.
So therefore, insulation is an absolute must. Insulation is an absolute must. We must calculate what is the thickness of insulation required based on the construction of the floor slab, and what is the temperature gradient from across the slab to the space. So insulation is an absolute must.
Okay. Thank you. I have another very basic question.
Yeah.
Suppose in a very small room, maybe in an official room, maybe 10 by 10, there is an room AC, there is a room AC, and we...
Shekhar bhai, I have accidentally muted you. Could you please unmute yourself?
Okay. So we have maybe there are two ceiling fans, and there is a 1 ton or 1.5 ton room AC. Actually, how this the contribution of this ceiling fan will be calculated in the room air supply as per standard 62.1?
So first of all, the ceiling fan will not contribute to any outside air. So if you have a room, whatever be the size, say 10 by 10 or 10 by 20, and you got a room air conditioner going, the advantage of the ceiling fan would be only one thing, sir, and that is you can raise the temperature of the supply air. Okay. So instead of setting the room thermostat maybe at 24 degrees Celsius, maybe you can think of setting it at 28 or 29 and have the ceiling fan going at a slow speed. Yes. So basically what you do is you increase the air velocity over your body, and therefore you feel comfortable at a slightly elevated temperature. Yes. So you save on power, but it is not going to improve the air quality. If you sleep in that room whole night, 1 or 2 people, then the CO2 level is going to build up. So what is the important thing here is that in such a case, if you're really worried, and you should be, about air quality, is that you must have an energy recovery ventilator, which will be a small fan, which is going to get air from outside, okay? And at the same time exhaust it. You get these very nice energy recovery ventilators nowadays. That is what you should really be using to make sure that you get outside air to come in. That is a must.
And yes, that ERV should be equipped with any filter?
You're getting the air from outside, it must be filtered. Yes.
Thank you so much. Thank you.
Right.
Thank you, Shekhar bhai, for your very nice questions. Our final question will be coming from Mr. Shahnood.
Thank you, Mr. Krishnan. I am Kazi Shanur from Bangladesh. So,
good evening,
please
sir.
tell you one thing is a very basic question. This was one room temperature is everything is okay, maybe under 20 degrees Celsius, and this time is continues doing like that. What is happening in the plaster and painting, and what is the effect about this plaster and painting due to the humidity?
Yeah, so what happens, that's why you need to be very mindful about what is the dew point in the room at all times. If your room is tight and you got no ingress of air, which is very difficult to say, you might have leakages. If you maintain the room at that kind of temperature, particularly in places like, say, Dhaka or, say, Bombay, where the outside is very humid, then you will have serious issues. You will have fungus formation, mildew formation on the wall, and that is going to create a lot of problems for you in terms of air quality. So you must make sure that the room temperature is running at, if you say you're going to run it below 20 degrees Celsius, it is rather cold for places like that. Because anytime you have any amount of leakage coming into the space, even if it's a small amount of air, I showed you those pictures where you had those air outlets with water droplets on them. That is exactly what will happen. So make sure that your room is tight, and you also must, now since it's not very easy for us to make rooms so tight that you will have absolutely no condensation, you want to make sure that you are operating the room at a few degree, maybe half a degree or 1 degree above the dew. That's the only way you can remedy the situation. Otherwise, you are going to have problems.
Thank you very much, Mr. Krishnan.
Thank you,
very
sir.
much.
Thank you, Mr. Shahnur Bhai. Our final question will be from Mr. Salman Kazi. That will be our final question.
Yeah, so Salman, please unmute yourself. Salman is an old friend from Qatar. So he's from
Good
Qatar
evening,
chapter.
sir.
Good evening, Salman.
I'm Salman Kazi from Qatar.
Yes, I
Sir,
know.
I have two small query related to energy efficiency and indoor air quality strategy. How to
Right.
reconcile between energy efficiency with indoor air quality strategy. And second, my small query is that if common office is there, and in that chill water air handling unit is supplying all over the office, and a small IT room is there, but IT room load is considerably high, like a sensible load is very high. So can we utilize CAV instead of a separate chill water fan coil unit? This is my second question. Yeah.
Okay, the first question is that where do we draw the line? Whether it's so Salman, you need to decide what's important for you. Whether you want to live your life well, or you only going to worry about energy. Because if you live well today, you can worry about energy tomorrow. But if you have issues because of air quality, then you're not going to be around to worry about energy. So for a long time, people have always been talking about energy. And I do know that back in ASHRAE, we keep talking about 90.1. But increasingly, people are focusing on air quality as something which is equally, if not more important than methods of energy conservation. So our idea is to try to see how we can optimize all of it together. That's why I said, for example, we must look at demand control ventilation. Can we do demand control ventilation to ensure that we are not wasting our resources, that we are making sure that we are providing the adequate amount of outdoor air required for people to be living well and to meet all the parameters. At the same time, we are not wasting energy. That's my limited argument on that point. The second point that you raised about having a high sensible load area, well, I don't know whether what you meant by having a CAV, because if you're going to have one common air handling unit to fill the IT, it might not be the best strategy, because your IT might be something that might be running 24 hours. Right?
Yeah.
So
Yeah.
in that case, it's always better to have a dedicated unit for that, because the rest of the office probably is not running 24 hours. So why do you run one
Correct.
big air handling unit for that? Doesn't make sense. So it
Yeah.
would be always proper for and appropriate that you have a dedicated unit for the IT, because first remember the off-coil conditions for the IT area as well as for the office spaces are going to be different. In an office
Correct.
environment, you might be working at a dew point of about 57, 58, whereas
Correct.
with this you'll be working at a very high sensible heat factor, right? So therefore
Correct.
have a dedicated unit just for the IT center and leave it alone, treat it separately. And for this, you need to worry about air quality. You need to worry about all the associated things, and also look at energy separately. So I think you will save energy when you kind of decouple these two and operate separately.
Correct.
Okay.
Okay, sir. Thank you. Thank you,
Thank
sir.
you. Thank you, Salman.
Thank you. We are not taking any more questions for now.
All right.
I'm going to give you heads up on our upcoming DL session. Fortunately, we have another session coming up very soon with Mr. Krishnan. The particular session will be on the Saturday, September the 13th, 7 a.m. Indian Standard Time.
7 p.m.
7 p.m. Indian Standard Time and 7:30 p.m. Bangladesh Standard Time. That would be on room air distribution. Coming
Okay.
up next on coming Tuesday, September the 9th, we are going to have another session with Teresa Western this Tuesday, 9 p.m. Bangladesh Standard Time. That would be on air leakage control and building envelope system more than energy efficiency. So that's all. And regarding the class recording, the recording of this particular session will be available in our Facebook group, ASHRAE Bangladesh chapter. Make sure you give us a like and get connected with our Facebook page so that you can access this particular very valuable class recording. Finally, I'm going to wrap up this session with a vote of thanks from Mr. Al Imran Hussain, President Bangladesh chapter.
Thank you so much, especially our honorable speaker. He is a nice guy, and also we have learned from in my previous webinar. I have attended several webinars from Mr. Krishna. So especially when we are in astrologers in India chapter also. So thanks also our audience, especially to attend our today webinar. So which are more effective for our local engineer, also other RL chapter. So special thanks to other RL chapter who are jointly or co-convener this webinar. So I hope all are enjoy and learn from lot from our expert. Thank you so much again from Bangladesh chapter. I hope next webinar will be meet with the same time and the same Bangladesh chapter. Thank you so much.
Thank you very much for having me. God bless you all, and I hope to see you again soon. Thank you very much.
Thank you
very much for a wonderful
Thank you.
presentation.
Thank
Bye-bye
you.
now.
Thank you, sir. Bye-bye.
Thank you. Bye-bye.